In 2026, implementing generative AI is rarely just pick a model and call an API. In production, you're implementing an end-to-end socio-technical system, a product experience, a data supply chain, an inference layer, and a safety plus compliance envelope that all evolve over time. That's why many teams ship impressive demos and then hit a wall when they meet reality. Access control, data cleanliness, latency budgets, model regressions, prompt injection, privacy constraints, and fees that look fine in a pilot but explode at scale. This report synthesizes primary and official sources to inform a pragmatic, production-first approach and to support a retention-optimized, technically credible, YouTube-friendly narrative. A useful mental model is that you are always making choices across 4 interlocking layers. At the governance layer, frameworks like NIST's AI Risk Management Framework, AI RMF 1.0, organize risk management into govern, map, measure, and manage functions, explicitly signaling that measurement and mitigation are ongoing lifecycle activities, not a one-time checklist. NIST's companion Generative AI Profile, NIST AI 601, exists specifically because generative systems bring distinctive hazards, like open-ended outputs, new misuse pathways, and integrity issues, requiring Gen AI-specific actions and controls. At the platform layer, you choose how you will serve models, self-hosted inference engines for control and potentially better unit economics at scale, or managed services for speed, vendor security posture, and operational simplicity. As concrete examples of the self-hosted serving ecosystem, LLM positions itself as a fast, easy-to-use library for LLM inference and serving, while frameworks like Ray Serve LLM focus on scalable production deployment patterns, auto-scaling, distributed serving, OpenAI-compatible APIs. For managed services, Amazon Bedrock describes itself as a fully managed service providing access to foundation models, while Azure's Azure OpenAI in Microsoft Foundry models and Google's Vertex AI documentation describe managed access, deployment, and lifecycle considerations for their model ecosystems. At the data layer, most enterprise wins come from context augmentation approaches, such as retrieval augmented generation, RAG, pairing a model with a retriever over a document store or knowledge base so outputs can be grounded in your organization's data. The original RAG research formalized this as a combination of parametric memory, model weights, and non-parametric memory, retrieved documents, to improve factuality and updatability. Modern product frameworks like Llama Index and Haystack operationalize this idea for production, explicitly describing RAG pipelines as a core pattern for building LLM apps over your data. Finally, at the safety security layer, the threat model for LLM applications is now explicit. OWASP's Gen AI Security Project maintains a top 10 list for LLM application risks, 2025 edition, including prompt injection, sensitive information disclosure, system prompt leakage, vector embedding weaknesses, and unbounded consumption, risks that map directly to real production failure modes and abuse paths, implementation architectures and deployment patterns that hold up in production. A high-leverage way to think about architecture is to start from the capability you need, then pick your augmentation strategy. RAG is the workhorse because it typically beats pure prompt engineering when you need domain-accurate answers with traceable sources, and it avoids the cost and complexity of retraining for every business update. In the RAG workflow, you ingest documents, segment them into retrievable chunks, embed them into a vector space, and retrieve relevant context at query time to ground the model's response, an approach reflected in both foundational research and production tool documentation. Where teams get stuck is not what is RAG, but how do I make it reliable? Retrieval quality is a first-order determinant of answer quality, which is why evaluation tooling increasingly measures the retrieval and generation steps separately. Ragus, for example, explicitly frames evaluation as component-wise. Assess the parts of the pipeline, not just the final response. Similarly, TrueLens highlights evaluating retrieved context, tool calls, and execution flow, and formalizes RAG triad checks such as context relevance and groundedness to build confidence against hallucination pathways. Beyond RAG, production systems often incorporate controlled tool use. The pattern is straightforward. The model generates structured intents, and the application calls deterministic tools, databases, APIs, calculators, internal services, then feeds the results back into the model for final language output. The danger is excessive autonomy. If you give the model unconstrained action power, you create a broader security surface, e.g., unauthorized actions, data exfiltration, cost blowups. This is why OWASP's 2025 list includes excessive agency and unbounded consumption, problems that appear precisely when tool access and execution aren't tightly governed. On the serving side, your deployment pattern is often shaped by latency targets and cost. If you self-host, you'll likely select an inference engine and a serving/orchestration layer. VLLM focuses on efficient serving, including innovations like paged attention and batching, and provides deployment guidance for Kubernetes. Hugging Face's text generation inference, TGI, is positioned as a toolkit for deploying and serving LLMs for high-performance text generation. If you want a local-first approach for smaller models or edge scenarios, Llama.cpp emphasizes minimal setup inference across a wide range of hardware and even supports an OpenAI-compatible API server mode. For larger-scale cluster serving and autoscaling, RayServe LLM provides a production framework for scalable deployment patterns, explicitly tailored for distributed LLM serving. If you're building on Kubernetes, you can integrate these engines into standardized serving systems. VLLM's docs describe deploying with Kserve for scalable distributed serving, and Kserve's generative inference docs describe a Hugging Face runtime that uses VLLM as an optimized backend for LLM workloads. This pattern matters because it separates responsibilities cleanly. Platform teams standardize deployment, auto-scaling, networking, and observability. Application teams build the product logic and evaluation loops. If you go managed, the differentiator is how much of the workflow your cloud provider can absorb. Amazon Bedrock positions itself as fully managed access to foundation models and also advertises capabilities like knowledge bases to implement RAG workflows, ingestion through retrieval, and prompt augmentation without building all integrations yourself. Google's Vertex AI documentation emphasizes Model Garden for discovering, testing, customizing, and deploying models on their infrastructure. Azure's documentation highlights Azure OpenAI resource creation and model deployment, and also flags that models are refreshed, deprecated, and retired as part of lifecycle management, an operational reality you must design for: fallbacks, canaries, eval gates. A final pattern that holds is model provider abstraction. Whether you're API first or hybrid, teams increasingly put an AI gateway in front of providers for unified authentication, routing, and cost governance. Light LLM, for instance, describes itself as an OpenAI-compatible gateway proxy to route requests across multiple providers through a unified interface. Governance, legal, privacy, and security constraints you cannot bolt on later. For data-driven product leaders, the hardest truth is that the limiting reagent of LLM implementation is often governance, not model quality. In the EU, the AI Act entered into force on August 1, 2024, according to the European Commission, but it applies in phases with different dates for different obligations. The official legislation is Regulation EU 2024-1689 AI Act, published on EUR Lex, which is the authoritative legal text, and should be treated as the source of truth over secondary summaries. Because modern product teams often use general-purpose AI models, GPAI, rather than training from scratch, it's also relevant that the Commission published a voluntary general-purpose AI Code of Practice on July 10, 2025, as a tool to help providers align with AI Act obligations, complemented by Commission guidelines on key GPAI concepts. Even if you're a downstream application builder, the practical implication is that you should expect more documentation requests, clearer provenance expectations, and stronger safety security requirements flowing through procurement and vendor risk review. On privacy, when your system touches personal data in the EU, GDPR principles and controls apply. GDPR Article 25, Data Protection by Design and by Default, pushes privacy into architecture choices, not just policy documents. GDPR Article 35 creates a formal obligation to perform a Data Protection Impact Assessment, DPIA, when processing is likely to result in high risk to individuals, highly relevant for LLM systems that may involve profiling, large-scale processing, or novel data flows. For AI models specifically, the European Data Protection Board, EDPB, has issued Opinion 28, 2024 on AI models, emphasizing that lawfulness issues in model development can affect deployment, and that analysis is case by case, given the diversity and rapid evolution of models. On security, LLM apps expand the threat model beyond traditional web risks. OWASP's 2025 Top 10 for LLM applications is one of the clearest, practice-oriented summaries of what to defend against, including prompt injection, sensitive information disclosure, supply chain risks, data model poisoning, improper output handling, excessive agency, system prompt leakage, vector embedding weaknesses, misinformation, and unbounded consumption. The implication for architecture is simple. Treat the model as an untrusted component. You validate inputs, constrain tool access with allow lists and sandboxing, assume outputs can be malicious or wrong, and instrument everything for monitoring and incident response. This is where guardrails become practical engineering, not a buzzword. NVIDIA's NeMo Guardrails describes itself as an open-source toolkit to add programmable guardrails to LLM-based conversational systems and explicitly frames mitigation of LLM vulnerabilities like jailbreaks and prompt injection as core use cases. OpenAI's Guardrails framework similarly positions itself as configurable input-output validation and moderation for LLM applications, implemented as a wrapper that can automatically apply checks. For privacy controls, Microsoft Presidio describes itself as an open-source framework for detecting and anonymizing sensitive data, PII, across text and beyond, useful when you need to redact or pseudonymize content before sending it to an external model. Finally, none of this works without observability. OpenTelemetry positions itself as a vendor-neutral open-source observability framework for instrumenting and exporting traces, metrics, and logs. Exactly the telemetry you need to understand latency, failure modes, user impact, and emerging risk patterns in LLM workflows.